SwayamPrabha. Digital India. Educated India.
So, we are now familiar with the three simplifications of the boundary layer flow model. The first one was the Stefan flow model, second was the Couette flow model, and the third is the Reynolds flow model. In today's lecture, I shall develop the Stefan flow model further for a variety of mass transfer problems that we encounter in engineering practice. The types of problems that we encounter are as follows. First is the inert mass transfer without heat transfer or chemical reaction. This means something like simple evaporation of water, where the water and the environment are all at the same temperature. So, there is no temperature gradient, and as a result there is no heat transfer, nor is there any chemical reaction, because water simply evaporates without any chemical reaction, and the mass transfer however takes place because of the concentration gradients. The next would be where, let us say, the water droplet or water itself in a lake is at a different temperature from that at the infinity state or the environment, in which case there would be heat transfer either to the water or from the water to the environment, depending on which temperature is larger. Then we will move to the situation in which there would be chemical reaction or combustion, in which let us say liquid droplet would be burning along with heat transfer from the environment to the droplet. And finally, but there we would use what is called as simple chemical reaction, and I will explain what that means. But many a times, particularly when dealing with burnings of solids, we need the reaction mechanism is so complex that we have to deal with that situation somewhat differently. So, I will develop the forms of mass transfer relationships that evolve for the four types of mass transfer problems. As you will recall, under steady state, the mass transfer equation would be something like this, n psi y a equal to all that, and psi can stand for the mass fraction or element mass fraction or enthalpy. The radiation term is of course neglected in this energy equation, and m dot double prime y k, as you will recall, is the diffusion mass flux as per the Fick's law of diffusion. So, these are the source terms in each of these equations. R k would be finite when there is a chemical reaction, if not it will be 0. So, let us consider the first type, inert mass transfer without heat transfer. So, let us say I have a tank here with water in it, and the water evaporates because in the infinity state the air is either dry or has a relative humidity less than 100%, and therefore, there would be mass transfer from water to the infinity state. The column height that I have considered above the water is L, and the air in the column is stagnant. Stefan flow model, as you know, is primarily applied to diffusion mass transfer. Both water and air are at the same temperature, and therefore, there is no heat transfer. Air also does not dissolve in water, as such there will be no transfer of air from the considered phase into the water phase. Steady state prevails, that is, water is supplied at the bottom at the evaporation rate. What this means is that somehow we have constructed an apparatus in which water is supplied at the same rate at which it is it is evaporating, and therefore, the column height L would remain constant or the water level will remain constant. Now, in this problem we have two spaces, one is the air A and the water vapor V, and therefore, the governing equation for this, because there is no chemical reaction, as you will see in the previous equation, NVYA would be equal to 0 for both air and water. So, that is what I have written here. This means that the mass transfer rate m dot w in kg per second would be area AW into NW is equal to A times NVY plus NAY equal to a constant, because this is gradient is 0. But in stagnant air, MAW is equal to 0, because there is no mass transfer of air in this, it is stagnant, and therefore, omega A plus omega V is equal to 1, of course, and we note this, and therefore, in this equation you will see that NAY will be set to 0 and m dot w would be simply A times NVY, and that is what I have written here. So, m dot w will be m dot of vapor only equal to A times NVY, and NVY, as you know, is the convective mass flux plus diffusion mass flux, and that would be equal to A rho m V, or if I rearrange this, notice that A rho m V is simply m dot w. So, therefore, m dot w into omega v minus rho m dA into d omega v by dy would be equal to m dot w, or if I transfer this on the right hand side, then you will see it will be 1 minus omega v equal to m dot w by rho m d dy by A, and if A is equal to A w is equal to constant, that is if I take the constant area model, then simply N w, which is equal to m dot w by A w, and integration would give me rho m d by L ln 1 minus omega v infinity over omega 1 minus omega v w equal to g star m into ln 1 plus b m. This bracket 1 minus omega v infinity into 1 minus omega v w can also be written as omega v infinity minus omega v w over omega v w minus 1, and g m star would be rho m d by L. It has the same units as the mass flux N w, and this is a constant, and when written in this form, B m is called the driving force for mass transfer to occur, and it is given in this fashion. So, you get a very simple logarithmic formula for mass flux or the evaporation rate, instantaneous evaporation rate of water. In the spherical system, supposing I have a droplet, then the surface area A would go on changing with the radius, and A would be equal to 4 pi r square as we go along, and A would go on changing. So, A would be function of y, if you like. So, in that case you will see d omega v 1 minus omega v would equal m dot w rho m d into dr by 4 pi r square. Integration from r equal to r w, which is the droplet radius, to r equal to infinity gives ln 1 minus infinity over 1 minus omega v w equal to this quantity with r w in the denominator. Remember, 1 over r infinity would be of course 0, and therefore, only r w survives. If I rearrange this equation, it would be written in this fashion: N w will be equal to m dot w divided by area of the spherical droplet 4 pi r w square would be equal to rho m d r w into this quantity, which again can be written as 1 ln 1 plus b m, where b m is again as before omega v infinity minus omega v w into omega v w minus 1, and g m star, which is the coefficient, if you like, is rho m d divided by r w instead of L in the previous problem when the area is constant. So, we get mass flux in this again a logarithmic form when area changes. So, both the results show that in diffusion mass transfer you get NW equal to G star m ln 1 plus Bm. But as Bm tends to 0, you can check out on your pocket calculator that ln 1 plus Bm tends to Bm for both positive or negative Bm. Thus, the linear variation NWG into Bm holds only for very small mass transfer rate Bm or NW, whichever way you want to look at it. Typically, when Bm is of the order of 0.02 or less, this relationship holds very well. And of course, when Bm is negative, then of course it will imply condensation. When Bm is positive, it would imply evaporation. Therefore, in general, we may write NW equal to GBm, where G over G star m is equal to ln 1 plus Bm by Bm, and where G star is the value of G when Bm tends to 0. Now, although this result has been found from for diffusion mass transfer, we shall later on show that the result has significance even in convective mass transfer. Let us now consider the case of inert mass transfer with heat transfer, in which case let us say the water and the environment are at different temperatures. So, let us say the temperature of the environment is greater than that of the surface, where Tw is the temperature of the water surface, and then under steady state, besides species conservation equation, we must now invoke the energy equation. And that, for as you will see from our first slide here, we are invoking this equation. So, dNVy HMA divided by dy would be d by dy of A Km dt dy, which is the conduction heat transfer, plus this is the fixed law of diffusion multiplied by Hk, which is in this case would be omega v by dy, H of vapor plus d omega A by dy, H of air, and the mixture enthalpy in this case would be the mass fraction of water vapor into enthalpy of water vapor plus 1 minus omega v, which is the mass fraction of air into enthalpy of air. Hv of course would be given by specific heat of vapor into T minus T ref plus lambda ref, which is the latent heat at temperature T ref, and Ha would have only the sensible part Cpa into T minus T ref, and the mixture specific heat would be simply omega v into Cpv plus omega air into Cp air. So, that is what this formula entails. Now, let us look at this term Km dt dy. Now, Km can be written as rho m alpha m Cpm dt by dy, and that is equal to rho m alpha m, and if I absorb Cpm dt dy and put Cpm equal to all this, you will see that you get omega v into dHv by dy plus omega A into dHa by dy. This result is an important one, which we are now going to substitute here. So, you will get dNVy HMA by dy equal to d by dy of rho m A alpha m omega v dHv by dy plus omega dHa by dy plus the second term, which is the fixed law of diffusion term, which carries with it enthalpy of the species. Now, in mass transfer problem, it is common to define Schmidt number as nu by diffusivity, and we define Lewis number as Prandtl divided by Schmidt number, which is equal to diffusivity of mass divided by diffusivity of heat. Now, for gaseous mixtures, Lewis number is very close to 1. For example, as you know, Prandtl number is about 0.7, Schmidt number would be about 0.67 to 0.68 in this kind of systems. So, in effect, Lewis number Le can be taken as very nearly 1, which implies that D is equal to alpha. D is equal to alpha. If I make that assumption, then you will see that and replace these rho m into D into rho m into alpha as gamma, as I have defined here, gamma mh equal to rho m D equal to rho m alpha m, then you will see this becomes gamma mh into A plus d by dy of simply product of omega v h v plus omega h a which is nothing but the mixture enthalpy dHm by dy. So, we essentially get d by dy NVY HMA equal to d by dy of this. Now, from species conservation, we have learned that NVY remains constant, which is equal to NW, the mass transfer at the surface itself remains constant throughout in a constant area problem. Then hence the last result can be written as d by dy of n NW Hm minus HMT minus gamma mh into d by dy Hm minus HMT, where HMT is simply the enthalpy of the transferred substance and it is a constant. So, all I have done is really added or subtracted Hm minus Ht and here Hm minus Ht, and therefore, I made really no change. So, HMT would be the Cp of the liquid into temperature of the transferred substance, which is water in this particular example, minus T ref is the specific enthalpy of the makeup water deep inside the neighboring phase. Cpl is the specific heat of the liquid. Now, this is again a conserved property equation in Hm minus Hmt. So, it is exactly same as the equation we had for omega v, and therefore, its solution too would be identical, Nw equal to G star Mh ln Hm infinity minus Hmt over Hmw minus Hmt, which I would write as G star Mh into ln 1 plus Bh in this case, where Bh is now formed from Hm minus infinity minus Hmw over Hmw minus Hmt, and G star Mh would be gamma Mh over Rw in case of a spherical system, and this would be the case in case of a linear system. So, we find that the logarithmic form is again retrieved from the solution of the energy equation, because just as we had recovered the logarithmic form in case of mass transfer without heat transfer. Now, since Lewis number is equal to 1, gamma mh would be equal to gamma m and gamma h, because thermal diffusivity is equal to mass diffusivity, and hence you will see Bh, which is Hm infinity minus Hmw over Hmw minus Hmt, would also be equal to omega v infinity minus omega Vw minus 1. Now, this relation provides the important link between the mass fraction of vapor at the wall and the temperature of the wall. Remember, when the temperature of the surroundings is at T infinity and the liquid, which is Tt, is at some other temperature, we still do not know what the surface temperature Tw will be, and we need to determine that in such problems. So, how do we determine that? We use this relationship, that is Bm is equal to Bh, and Hmw would be then Hvw omega Vw Haw into 1 minus omega Vw, and if I take T ref equal to 0, then Hmw will be simply Cpa into Tw into Cpv minus Cpa Tw plus lambda at 0 degree, lambda at T ref equal to 0 into omega Vw. So, hence for a given T infinity and Tt, the Bm equal to Bh relationship will iteratively give omega V and omega and Tw. So, what one does is one simply assumes a value of Tw. Hm infinity of course can be obtained, because you know already omega V infinity, you know T infinity, and therefore, that can be obtained. This too can be obtained, as we saw on the last slide. This can be obtained knowing Tw, only thing is you do not know omega Vw. So, how do we get that omega Vw? We can get that by saying that at the surface of the water, saturation conditions would prevail, and corresponding to RH equal to 100%, and therefore, that value of omega Vw can be noted either from the psychrometric chart, or you can also use steam tables, in which case you will get a partial pressure, so that from which you can recover the mass fraction of the wall. If after assuming Tw you have determined omega Vw in this way, you substitute in the Bm expression. If you find that BH is equal to BM, then obviously your choice of TW was correct, and therefore, you already have TW omega VW relationship. If however, the two equations do not balance, then you must change the value of TW till you get balance between BM and BH. So, iterations are involved in discovering temperature TW. Now, in order to help, if you are doing something on the computer, then for air water vapor mixture, saturation condition, that is the saturation curve on the psychometric chart is given like this, where this is the T dry bulb and this is the specific humidity, and you have the 100% RH line. So, the values corresponding to this have been correlated here in omega VW as a function of TW for the range of TW minus 20 to 100. And for computer applications, in order to help iterations, one can use this relationship or simply try by hand. This is just for your information. So, now of course, when you consider a fuel, we do not know the omega VW TW relationship by way of a psychrometric chart or anything like that, and therefore, such a relationship must be determined from what is called the Clausius-Clapeyron equation. And in that case, you will see that omega VW is related to XVW into molecular weight of vapor divided by molecular weight of the mixture, and XVW of course is equal to P saturation at TW divided by P tot. XVW would be given by exponential of minus HFG divided by RG into 1 over TW minus TBP. For all liquid fuels, typically you will have a boiling point known and HFG known, and therefore, XVW can be recovered for a given TW. So, one tries in such cases assume a TW, recover a calculate XVW, from that you calculate omega VW and check whether BM is equal to BH as on the previous slide, or otherwise go on changing TW till you get convergence. Now, I turn to the problem of mass transfer with heat transfer and simple chemical reaction. Now, what is simple chemical reaction? Let us consider a highly volatile liquid fuel that burns in the considered phase according to the simple chemical reaction SCR. Liquids usually burn by first evaporating in the gas phase without any change in composition, that is, the chemical formula of the fuel does not change when it comes out in the form of a vapor, but then it burns in the vapor phase as a gaseous phase as a homogeneous combustion. And we say that simple chemical reaction simply implies that 1 kilogram of fuel combines with RST kilograms of oxygen to give you 1 plus RST kilograms of products. Now, where RST is the stoichiometric ratio of the fuel, and you must have learned from your stoichiometry how to evaluate, say for example, a hydrocarbon fuel, how to evaluate the value of RST. Now, in this problem therefore, we have three species: the fuel species, the oxygen species, and the product, which is itself a mixture, but it is a product species, we take it as a single species. Then we will have three equations, and because the chemical reaction is present, you will have convective flux and a diffusion flux. d by dy of would equal rate of depletion of fuel. Therefore, I have said magnitude of RFU with a negative sign. Likewise, oxygen too would deplete minus RO, whereas the product would increase, and therefore, it has a plus sign in front of here. So, we have three equations because we have three species with three mass transfer equations. If we add the three, we must retrieve the bulk mass conservation equation, because the addition of the fuels, fuel, oxygen and product, sum of these will be equal to 1, and when all these are summed, that will be equal to 1. So, d1 by dy would be 0. So, all sum of the diffusion fluxes would add to 0. and therefore, you will be having A n w d by dy of n w into sum of all these quantities, and therefore, the sum of the R k must also be equal to 0, because the bulk mass conservation. So, therefore, SCR simply implies that RO2, the oxygen depletion rate, is equal to RST times fuel depletion rate. Where on the other hand, the product generation rate would be minus 1 plus RST times fuel depletion rate, and likewise the diffusion of oxygen would be RST times m dot F double preview, and product will be 1 minus 1 plus RST m double dot Fu. So, if I now divide this equation by RST and then subtract the resulting equation, I divide by RST throughout, and which is a constant, and subtract that equation from this equation, then you will see that RFU minus RO2 divided by RST would be of course 0, and as a result you will get an equation which is like this: d by dy of A n w phi minus gamma m d phi by dy equal to 0, and phi will be omega Fu minus omega O2 by RST. Likewise, if I divide this third equation by 1 plus RST throughout and add, then again the right hand side would 0, and I will have a phi which will stand for omega Fu plus omega product over 1 plus RST. And we said that any equation of this form with the 0 source term implies that phi is a conserved property. So, we have again got an equation of conserved property like the inert mass transfer problem, and therefore, we would have n solution of that would be n w equal to g star m ln phi infinity minus phi t over phi w minus phi t equal to g star m ln 1 plus b m, where b m would be given now by this quantity phi infinity minus phi w over phi w minus phi t, and phi can stand for this group or it can stand for this group. Then one uses the appropriate group depending on the convenience of the problem at hand. G star m would be of course gamma m divided by R w in a spherical system, or gamma m divided by L in the plane system. The important thing to note is that even in a problem involving combustion, we are able to reduce the problem mathematically to a form just like that of a evaporation of water in the absence of heat transfer. So, let me now turn to energy part of the because whenever combustion takes place, there would be heat transfer. So, now we would have d by dy of A n w h m minus k m dt dy would equal d of the diffusion mass transfer of dy. You remember from slide 1, this is the right hand side, and this is the equation that I am writing now. This is the energy equation then equal to the right hand side. This is the right hand side, where H sub k is the species enthalpy, and as you will know that whenever you have reacting fuel, we write it as H naught F k as the enthalpy of formation plus C p k into T minus T ref, or for the short I will write as H naught F k C p k delta T. So, hence making use of definitions of phi, let us say H m would be simply omega k H k, and therefore, it will be omega k H naught F k plus delta T into sigma C p k omega k. Then the first part of the term would simply result in omega F u H naught F u plus omega O 2 H naught F O 2 plus omega product into H naught F product, and C p k omega k would be simply C p m, the mixture specific heat, into delta T. Now, from the previous slide, we have defined phi. So, I can say that omega over 2 by R s t will be minus omega product over R s t. So, that is what I am going to use here. So, I am replacing omega product by 1 minus R s t over R s t omega O 2 equal plus C p m delta T, and omega O 2 itself would be equal to omega F u R s t into all this, and as a result you will see I get omega F u into H naught F u plus RHT H naught O2 H naught F O2 minus 1 plus RST H naught F product plus CPM delta T. This essentially means that this is the enthalpy, total enthalpy of the reactants. 1 mole of fuel combines with RST moles of oxygen. Therefore, this is the enthalpy of the reactants and this is the enthalpy of the product. So, the reactant enthalpy minus product enthalpy, as you know, is the heat of combustion, and therefore, you will get omega Fu del Hc plus Cpm into T minus T ref, where delta T is written as T minus T ref again, as I said there. So, we get a enthalpy equal to heat of combustion into omega fuel. Now, of course, I have here replaced omega O2 and omega product in terms of omega Fu, but I could do it the other way. I can replace omega Fu and omega O2 in terms of omega product, or I can replace omega Fu and omega product in terms of omega 2, and I will get different expressions involving del Hc, which I will show you shortly. But now, let us consider the right hand side, which is minus d by dy of A sigma k myk hk. So, here summation of k m double prime yk hk would be simply H naught Fu Cp Fu delta T into, this is the expression for my Fu, plus the same quantity for oxygen and the same quantity for product. Now, we make an important assumption, which is always made. Now, for gaseous mixtures, specific heats are functions of temperature, and for different species they are somewhat different, but they are not so different that we cannot make an assumption of equal specific heats. And if we assume that this each species has the same specific heat, then it would simply equal the mixture specific heat. So, that is the assumption I am going to make and use the stoichiometric relation omega O2 equal to RST Fu, omega Fu and omega product equal to minus 1 minus RST omega Fu. And if I do that, then this entire relationship can be written as minus del Hc rho md omega Fu by dy, because Cpm delta T into sigma k d omega k by dy would, because sigma omega k would simply add up to 1, and that is equal to 0. And also from the previous slide, we have shown that Cpm dt by dy is equal to dHm by dy minus, remember. So, if I take differential of this equation with respect to y, then the Cpm into dt by dy would be dHm by dy into minus del Hc into d omega Fu by dy, and that is what I have written here. So, now I have this expression and I have this expression, which I am going to make use of in deriving the right hand side. So, the right hand side can now be formed, which is, as you know, is d by dy of. So, I can now take everything on this side, and you can see that I can transform this equation into A times NWHm into Km by Cpm dHm by dy minus del Hc d omega Fu by dy. This is essentially the k dt dy term. This is the del Hc rho md d omega Fu by dy, which is the right hand side term. And then if I again make the Lewis number equal to one assumption, that is alpha m equal to d, then you will see that gamma m, this Km by Cpm can also be written as rho m into d and equal to gamma h, let us say. So, then you will see that this term would get cancelled with that term, and I would get A times NWHm gamma h into dHm by dy equal to 0. And again a conserved property relationship has been obtained from the energy equation. So, the solution would be again same as that for inert mass transfer, with BH defined as Hm infinity minus HMW, HMW minus HMT, and this is the G star MH. So, again you will see that in a simple chemical reaction we have got the same formula both from mass transfer equation as well as from the energy equation. So, as I said earlier that we can define our mixture in variety of ways for a simple chemical reaction. One is to say HFU is equal to CPM delta T omega FU del HC, which is what I did earlier. HO2 will then be equal to CPM delta T and H product will be CPM delta T because of the equal specific heat. But I can also associate del HC with oxygen, in which case HFU will be CPM delta T, HO2 will be CPM delta T into omega 2 O2 RST del HC and H product. And then again you have HFU, HO2, and I can associate now with omega del HC with the product mass fraction. So, there are three ways in which you can do it. For a liquid fuel burning in air, we often choose second type because we often know omega O2 concentrations much better. So, then HM will be omega K HK would be simply CPM into T minus T ref omega O2 by RST del HC, which is from these three relationships. And if I now take for a moment that T ref is equal to TW, which I do not know usually, then I will get, for convenience rather than not knowing, where T ref, if I take T ref equal to TW, then BH, which was HM infinity minus HMW over HMW minus HMT, would transform to CPM T infinity minus TW del HC omega O2 infinity minus omega O2 W divided by RST del HC into omega O2 W by RST minus CPL TT minus TW, where of course omega O2 T is 0 because oxygen does not exist in the fuel, and TT is known or knowable somehow. If TW was already, if the fuel surface was already at the boiling point TW by TBP, then of course no oxygen would survive at the surface, and therefore, that would be 0. That would be 0 because the fuel concentration there would be 1. If TW is not equal to TBP, then of course, omega O2 and TW relations must be established iteratively by balancing BM and BH, where BH is given by this. So, you assume a TW, evaluate the BH value, then evaluate the BM, then evaluate the omega VW, rather omega O2W, and then again get the balance done in favor of till convergence is obtained, where BM is given by this relationship, and you will see phi value now will be known in all states. For example, omega FU in the infinity state is 0, whereas omega 2 is known. So, phi infinity is known. In the T state, omega FU will be 1 and omega O2 will be 0. So, phi T is known. Omega W will depend on the temperature, which will determine omega FU, and the remaining will be omega O2. So, we can determine the relationships in that manner and carry out iterations. Now, I come to mass transfer with heat transfer and arbitrary chemical reaction. What do I mean by arbitrary chemical reaction? By arbitrary chemical reaction, this typically occur in solids combustion. So, for example, let us say consider burning of a graphite C star given by C star at very high temperatures TW of the order of 1950 or much higher. Then there are several reactions taking place. The first 4 reactions take place at the surface of the graphite, C star half O2 equal to CO, whose equilibrium constant is infinity. C star CO2 would be 2 CO, whose in again Kp is 4000. C star H2O equal to CO plus H2 1230, and C star equal to 2H2 equal to CH4 1 by 790. CO thus generated and hydrogen and CH4 would then burn in the gas phase. Of course, here the Kp is so low at 1950 that hardly any CH4 would be formed, and therefore, we can say that very small amounts of CH4 will be present. CO would then react with oxygen to produce CO2, which would then dissociate in this fashion. CO2 will be CO plus half O2 giving you CO2, and H2O would dissociate to give you H2 plus O2 Again, the Kp is very low, and therefore, the reverse reactions would be dominant, producing CO2 and H2O. So, for such a complex mechanism, it is best to conserve the elements. We have elements C, H and O in this case. You can see elements are C, H and O. Of course, nitrogen is not present in the fuel, and therefore, we write this, and as you recall, the element mass fraction equation is always a conserved property equation. So, let the infinity state comprise of CO2, H2O and N2 only, that is the full products. So, the noting the equilibrium constant Kp for each reaction, it can be shown that in the considered phase CH4 cannot survive in appreciable magnitudes. Hence, it will comprise, the considered phase will essentially comprise of CO2, H2, CO and H2O only. Similarly, in the W state, only CO and H2 will survive. And therefore, since species change in different states, it is best to define a eta C equal to omega C star over 12 by 44 omega CO2 equal to that, eta H would be given by that, and eta O it will be given by that composition. Thus, we have three equations for eta C, eta H and eta O. So, instead of solving three equations, we need any one can be solved, but you will find that not all these quantities on the right hand side are very well known in the three states. So, the best thing is to derive a composite quantity, which we shall take as eta C minus 3 by 4 NO, and from this relationship you will see that I can form a new variable omega C minus 3 by 11 omega CO2 minus 2 by 3 omega H2O. Now, I can definitely form phi W equal to NC minus 3 by NO W equal to 0 in the W state. In the T state, only eta C will be 1 or omega C will be 1. All these are zeros. So, they are put to 0, and in the infinity state I do not have any carbon, but there is omega CO2 and omega H2O. So, they are retained, and as a result I will get NW equal to ln 1 plus Bm, where Bm would be 3 by 11 CO2 infinity plus 2 by 3 omega H2O infinity. Both these are known in the infinity state, because that is what we said, that we know only the products in the infinity state. So, and therefore, I can calculate the mass transfer rate of graphite burning simply by knowing CO2 in the infinity state and omega H2O in the infinity state. So, in this case, because I know the relationship connecting element mass fractions with the species mass fractions, I am able to create a composite phi as eta C minus 3 by 4 simply by observation. This manipulation is simply by observation, such that I do not want any of the things, any species on the right hand side whose concentration I would not know in the infinity W and T states. And this is what I have been able to achieve, so that the calculation of mass transfer becomes easy. So, in summary, I would say that we have analyzed all types of mass transfer problems by converting every problem to a conserved property equation, and psi has to be defined appropriately, so that N W equal to G B with G by G star equal to ln 1 plus B by B, and B is equal to psi infinity minus psi W over psi W minus psi T, and A is 4 pi r square or a constant. Now, for inert mass transfer without heat transfer, psi was equal to omega phi, as you know, and gamma was simply equal to rho m d. For inert mass transfer with heat transfer, we had psi equal to omega v and h m, and we made the assumption of Lewis number equal to 1. For inert mass transfer, for mass transfer with heat transfer in chemical reaction, we choose psi equal to appropriate phi and mixture enthalpy. We make the Lewis number equal to 1 assumption, and also we say that the specific heat of participating species would be equal to specific heat of the mixture. And in the mass transfer with arbitrary chemical reaction, we showed that psi can be simply appropriate phi and gamma m as rho m diffusivity. So, you can see that a variety of problems have been reduced to conserved property relationship through appropriate and justifiable assumptions, which makes calculation of the mass transfer rate simple, and we are able to derive analytically derived relationship connecting NW, the mass transfer, to the driving force B, and the relationship we found is a logarithmic one. In the next lecture, we will see what the Couette flow model has to say.